So, as you can gather from what Adler writes as a preface to his book, um, his idea is to derive quantum theory from an underlying classical theory of random matrices which obey arbitrary commutation relations and which have a certain global unitary invariance which gives rise to a very remarkable conserved charge which is not there in ordinary classical mechanics. I'll say these things maybe again and again. So the underlying theory is a classical dynamic theory obeying the usual dynamical laws of let's say Hamiltonian dynamics or Lagrangian dynamics, but is different from classical mechanics. And this is the book. So, okay. Firstly, I should say that most of this talk is based on our condensed review. So if you would like, you can just note down this number. And if you have a laptop, you can even go to this paper on the archive just now, because it has more details than I can show in my talk. It has more equations, so you can keep referring there if you like. It's to a large degree a cut and paste from that article, so following would not be difficult. Also, the slides are also already on the program web page. So if you like, you can open one more window and browse through those slides, go back and forth if you want to find out what was said earlier, etc. And more details are available in this very nice book Adler wrote in 2004, summarizing 20 years of work. It's called Quantum Theory as an Emergent Phenomenon. This is also available, at least parts of it, on the archive. The archive number is there in the abstract that I have put on the website. So these are the two main references. And then there are the original papers, around 10 papers by Adler and collaborators, where this whole idea was developed. Okay. So we can say that the relation between trace dynamics and quantum theory is analogous to the relation between statistical mechanics and thermodynamics. Just as we start from an underlying microscopic theory, let's say in the Boltzmann sense, and do its statistical mechanics to arrive at its thermodynamic properties. In the same sense, trace dynamics is like the underlying classical microscopic theory, whose statistical mechanics in thermodynamic equilibrium leads to quantum theory. That's the claim. There are quite a few caveats along the way, which basically means the theory needs to be understood better. So those are gaps in understanding, not loopholes. And I should also explain along the way why this is not the so-called hidden variables theory, because when you all start of thinking of deriving quantum mechanics from a classical theory, the first reaction is unease, that is, are there hidden variables? We'll try to understand why those no-go theorems of hidden variables do not apply here. So now we divide these two talks into three parts. Step 1, Step 2, and Step 3. Step 1 is the classical dynamics, as I just said. It's a classical theory, which is a classical dynamics of non-commuting matrices. Grassmann valued, will come to what are Grassmann elements. These are numbers which don't which anti-commute with each other. They have been brought into the picture to deal with fermions. Fermionic operators have anti-commutation relations. That's the main reason for bringing in Grassmann numbers. But that's a bit of a side story, though it might look like the key thing. In principle, you could have worked with the complex numbers instead of complex valued Grassmann numbers and gotten to the same result, but that would be a quantum theory or a quantum field theory of bosons, Adler's just doing complete job keeping fermions in the picture. So again, part of the classical dynamics is this very important central theme to the whole project, that the Lagrangian and the Hamiltonian of the theory have a global unitary invariance, as a result of which there is a conserved charge, which we will come to, which I'll talk of again and again, because which is essentially what is responsible for the emergence of the quantum theory. So which is what makes this dynamics different from point particle mechanics, the existence of this conserved charge, which is not there in point mechanics. Okay, step 2, as I said, in the conventional sense, we will construct the canonical ensemble for this underlying microscopic theory. This is absolutely conventional statistical mechanics, except that because of the presence of that so-called conserved charge, interesting new features will emerge. So we'll derive the equilibrium theory, the thermodynamic equilibrium. Then, in the spirit of field theory, we will derive an important word identity, which is a consequence of assumed invariance in phase space of canonical averages under constant shifts in phase space. This is analog of equipartition theorem in stat mech, so please remember it that way. And once we do that, once we derive this so-called equipartition theorem, it turns out that the thermodynamic averages of dynamical variables obey quantum theory. So the underlying theory, there are no well-defined commutation relations. Position, 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 momenta, 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 all have random commutations with each other, and commutation or anti-commutation relations. But when you do the thermodynamics of this classical theory, the stat mech of this classical theory, the canonical averages, the thermally averaged quantities obey standard commutation relations of quantum theory. They obey the Heisenberg equations of motion. And from there, one can go to the equivalent Schrodinger picture in the conventional view. So this is the layout, and there is now also a step 3. Thermodynamic equilibrium is quantum theory, but we should also worry or consider fluctuations around thermodynamic equilibrium, like described by Brownian motion. It turns out that when you do that, when you find out how the equilibrium, how the fluctuations around the equilibrium modify quantum theory, you get nonlinear stochastic modification of the Schrodinger equation, which helps to resolve the quantum measurement problem and derive the Born probability. There are caveats there. It's not 100% neat. Adler also knows that. He talks about it in the book. But this is the spirit that the so-called collapse models, which Angelo will talk about tomorrow, which are a phenomenological modification of the Schrodinger equation, which is expressly constructed for solving the measurement problem. The collapse models can in principle be derived from trace dynamics by considering fluctuations around equilibrium. The spirit, at least, is, I think, very nice. A classical theory is thermodynamics, is quantum theory, is fluctuations around the thermodynamic equilibrium are modifications which lead to nonlinearities, which in principle can solve the measurement problem and make contact with the collapse model. So these are broadly 3 steps, if you have any questions. So now we just try to fill in details. Okay, step 1, what is the classical dynamics? as I said, the fundamental degrees of freedom are matrices which live on a background space-time, and the elements are complex valued Grassmann numbers. Okay, so there will be an algebra, there will be an algebra of Grassmann numbers, a Grassmann algebra over complex number coefficients. And what are Grassmann variables? They, as I said, they have the following properties. If you have two of them, theta I and theta j, they anti-commute, unlike ordinary real numbers. So obviously the square of a Grassmann variable is 0. And you can construct a complex Grassmann number chi, which is theta r plus I theta I, where theta r and theta I are just two ordinary Grassmann elements satisfying this anti-commutation relation. And clearly the anti-commutator of any two chi's will also vanish. And okay, so as I said, this is a bit of an excess baggage for the main theory. They are there on the scene, Grassmann variables are there on the scene to take care of fermions. They are not central to the theory, doesn't depend on having Grassmann numbers. You could still do this whole project with the ordinary complex numbers. So we'll make matrices. Before that, so given these Grassmann variables, you can make an algebra by, there's a sum of Grassmann numbers, they're products of different Grassmann numbers, etc. You have a algebra over these Grassmann variables, and Grassmann numbers are the elements of these matrices, which as Edward says, you deal with finite dimensional matrices of arbitrary dimensions, but in principle the dimension could be let to go to infinity. It's not a matter of concern for this construction. Okay. Grassmann elements, these elements of these matrices have other important properties, as you can easily verify. If you have a product of even number of Grassmann elements, Grassmann variables, at theta 1, theta 2, it will clearly commute with theta 3. So theta 1, theta 2, theta 3 minus theta 3, theta 1, theta 2. So you can move them through each other, and every time you exchange, there will be a minus sign. So if you exchange even number of times, the minus sign goes away, so the commutator vanishes. So if you have a product of even number of Grassmann elements, they commute with everything. They commute with other even number, and they commute with odd number, also with those elements which are a product of an odd number of them. So these are going to behave like bosonic degrees of freedom. And product of an odd number of Grassmann elements anti-commutes with any other odd number product. If you have theta 1, theta 2, theta 3, it will anti-commute with theta 4, because when you move them through each other, you will have an odd number of sign exchanges, so the anti-commutator will vanish. Okay, so what this means that we have, over the Grassmann algebra, we have two disjoint sectors. The bosonic sector B is what is above called 1. It consists of the identity and even grade elements of the algebra. It's a subspace which is closed. If you are in that subspace, you stay there. Similarly, you can have the second one is called the fermionic sector. It consists of odd grade elements of the algebra. So we have divided the algebra into two parts, the bosonic sector B and the fermionic sector F. So bosonic sector, as I said, even number products of Grassmann variables essentially behave like complex numbers, ordinary complex, in terms of their algebra properties. And okay, so far so good. As I said, it's arbitrary. if you think of them as operators, you may have some representation. So the dimension is not something of consequence in the. Yes, yes, I should have said that. Very good point. Space-time in this theory is ordinary. Flat, in fact, flat space-time, there is no gravity. There is no matrix degrees of freedom for space-time. Only matter fields are being treated. Okay. So that's a good point that eventually, why should gravity not be brought in? We'll talk about that tomorrow. Yeah. What does it mean? What does it mean? If you look at the point 1 above, you understand a Grassmann number is a product of even number of elements. That is commuting with anything else which has even number. So all such Grassmann numbers which are product of even number of elements, you make a set out of them along with the identity. They will live with each other. So they all have the same property. So that's the bosonic set. Sorry, I think you're asking. If you don't, sorry? To bring in fermions. Yes, yes, you could live without Grassmann numbers. In fact, that was how the project, it seems, was first done. It was done only for bosons, yeah. No, no, at every space-time point there is a matrix. Yes, yes. No, it depends, it's up to you. You can have n Grassmann elements and let n go to infinity. Yes. You can go to a continuum also, but for the time being we don't do it. Okay. Where? Here? Yeah. No, odd also. That you can check. Just the theta 1, theta 2 will commute with theta 3, the product theta 1. Yes. Yeah, but because, odd anti-commutes with odd, so you want to keep them together. Because suppose you keep an odd here in the first sector, you keep another odd, those two will anti-commute. You have clubbed only the first kind because these all commute with each other, like bosonic degrees of freedom. And separate bosons and fermions. Okay. So the fundamental degrees of freedom, as I said, are matrices made out of elements from these sectors. You can have bosonic matrices, which will be made out of even grade elements. You can have fermionic matrices, which will be made out of odd grade elements. And a general matrix can be decomposed as sum of two matrices, one which is bosonic and one which is fermionic. So we'll basically keep these separate from now on. Okay. We can define in the ordinary matrix trace sense a trace on this matrix field from a matrix, basically sum the diagonal elements, and that will be a complex valued Grassmann number, that is this field GC. Trace is going to play an important part, hence one of the reasons why the theory is called trace dynamics. Another name was generalized quantum dynamics or pre-quantum theory, precursor to quantum theory. Okay. Now this is important. We are going to do make a Lagrangian dynamics out of this. The Lagrangian, we don't want it to be a matrix. You much rather think of it as a trace with certain additional property, like the trace should be a real number. Those kind of things will be assumption. So we need to work with traces, and when you derive equations of motions from the Lagrangian, let's say by varying it with respect to operator or a position operator Q, which is now operator or a matrix, we have to worry about how to differentiate a trace with respect to an operator. Yeah, we need that for the dynamics. So that's why this notion of a trace derivative. It turns out this actually goes back to the early days of quantum theory. The idea of trace derivative was first talked of by Born and Jordan in 1925 in the context of Heisenberg dynamics. It kept appearing in a few papers in the following decades, but never really picked up to be something important until Adler and collaborators caught on to it. So most of the classical dynamics of random matrices using the trace derivative concept, this has really fully been developed for the first time by Adler. Okay. Given a polynomial P, made out of, let's say, non-commuting matrices, one of which, let's say, is O, we form the trace of P. So P is a polynomial in matrices, a matrix product. You can get the trace of that polynomial, call that trace P, denoted by this symbol bold P. Now the following is a definition of the trace derivative of this trace quantity P, which is in general, complex valued Grassmann number. How do I define this derivative with respect to the variable O? That is done in this first line here. But we'll go through it a little slowly because it looks funny. Delta P by delta O is the trace derivative of P with respect to O. How is it defined? That's probably best seen with the elementary example. Let us look at this polynomial A, O, B, where A, O, and B are any three Grassmann valued matrices which do not commute with each other. And I want to find the derivative, the trace derivative of P with respect to O. So you could have other monomials in which O appears more than one time, say A, O, B, O, C, O, blah, blah. So same idea will apply. So the variation of P is going to be A delta O times B. Now let's take the trace of, so I want delta trace P. I want in the next line, the variation of trace P, which is the same as this bold trace P. Variation of trace P is trace of variation of P, and trace of variation of P is trace of A delta O B. Yeah? Just take the trace of the delta P. Now the important part is, whenever you have a delta O sitting somewhere, move it to the extreme right to a cyclic permutation inside the trace. there are a whole lot of identities which I have not written down, which are trace identities, trace bilinear and trilinear identities. If you have a product of bosonic and fermionic matrices inside the trace, it obeys cyclic identities, which if you have the article open, you will find a list of these cyclic identities. So we have to always do a cyclic permutation inside the trace in such a way that delta O, the way one operator with respect to which you are finding the variation, must always come and sit on the right. So we move B to the left inside the trace, you have BA delta O, but when you do that cyclic permutation, the identities tell you that you may or may not change sign depending on, say, whether B is bosonic or fermionic. That's why this symbol epsilon B. If B is a bosonic operator, epsilon B is +1, and if it is a fermionic operator, epsilon B is -1. Okay, so now we have everything. You take the epsilon B inside the trace. You trace epsilon B BA times delta O. So if you compare with the first line, here, oops. Yeah, if you compare with the first line, you have a trace of delta P by delta O times delta O. Delta P by delta O is the definition of the trace derivative. Whatever is sitting inside the trace to the left of the variation delta O is the trace derivative. So you can read that off here. The trace derivative of P with respect to O in this example is epsilon B times BA. So this is important because at least in principle this will be used again and again, though we won't see much. What we are going to do is formal stuff really. I won't show much calculation. Yeah. Yeah. No, you can. It's a Leibniz rule. You suppose you have A O B O C. The variation is A delta O B O C plus A O B delta O C. The Leibniz rule, and then you do it for the. It's +1 if B is a bosonic operator, -1 if it is fermionic. It is coming from the properties of the cyclic identities of the trace. Okay. All right. So what is yes? So we for this work we will work with the traces P to define the dynamics. Okay. And again, just to simplify life, we'll work with polynomials P which are bosonic because we want, real valued traces out of them to make things like Lagrangian and all. That's if you have a polynomial which is fermionic, you can always go from a bosonic to a fermionic polynomial by multiplying by a suitable constant Grassmann matrix. So that's not much of a problem. All right. The definition delta P equal to A delta O B. Variation with respect to O. Yeah, so go to the second line. You take trace of delta P. There is delta trace P. The last line, trace P. Trace P is bold P. Trace P is defined as bold P. You look at the very top, the third line, the definition that trace P will be denoted by this symbol bold P. You get it? The last line. In the example, delta P is trace delta P by delta O, that one. No, that is correct. That's the definition of the trace derivative. It is defined this way: inside the trace, whatever is sitting to the left of delta O shall be called the trace derivative of P. Yeah, it looks funny, but it's correct. It looks as if you have put two traces, but it's correct. Yeah. Bold P is trace P, yes. So just see, what is inside the trace here? BA. So, whatever is inside the trace shall be called the trace derivative. Compare this with this. Okay, maybe just look at the article, look at Adler's book. All right. So now I want to make the dynamics out of this. In principle, fairly straightforward, just like classical mechanics. We think of the Lagrangian as a Grassmann even polynomial function of bosonic or fermionic operators and their time derivatives. And we take the trace of this polynomial, which is this boldface L. Okay. Now, what are the degrees of freedom? Those are configuration variables QR and their time derivatives QR dot. What is important to remember is that these Q's do not commute with each other. They have arbitrary commutation relations. That makes it different from the configuration operators in quantum theory, obviously. Any two Q's, if they are bosonic or even fermionic, they commute or anti-commute, yeah? That's the difference. We'll define momenta also. The momenta also don't commute with each other, and the position and momenta also don't commute. And non-commutation is arbitrary. It's not QP commutator equals IH bar. It is QP commutator equals anything. Or if it's fermionic, the anti-commute. We'll assume, this is an assumption, that the action that we construct and the Lagrangian, trace Lagrangian that we construct are real quantities. This is a constraint imposed on the choice of the underlying Lagrangian polynomial. You can vary this trace action with respect to these configuration variables using the trace derivative concept. And we'll again get Lagrange equations of motion. You can define a canonical momentum P in the standard way. Now, what is important here is that since it can be shown, since L is, the Lagrangian is made from Grassmann even polynomial, when you vary it with respect to Q, if Q is bosonic, P will be bosonic, and if Q is fermionic, P will be fermionic. You can define the trace Hamiltonian in analogy with the classical definition of the Hamiltonian. No, Q are operators representing configuration degrees of freedom. That could be one matrix. It's like instead of a point particle Q, I have a matrix. Q. You could make it out of some polynomial, but I wouldn't want to think of it that way. Rather, the polynomial, the Lagrangian L, is made out of these Q's and Q dots. Yes, yes. These are positions, matrix position. Time derivative of each element, yes. Or like in the operator sense, like in the Heisenberg. Except that these are not Heisenberg equations of motion, as you can see. These are classical equations of motion. The Hamilton equations of motion follow from this trace Hamiltonian. And there's in the second equation, the epsilon r that comes because of the, bosonic or fermionic nature is +1 for bosons and -1 for fermions. One is bosonic. The trace behaves like a complex number times a even number product of Grassmann. And if you assume L to be self-adjoint, the trace will become real. Yes, yes. If you want to, have a Lagrangian or action which is a real number, it's a constraint. So I should point out, as Adler says, this is not a specific theory, it's a formalism. A specific theory of nature should tell us what is my L. Particle physics motivated L should be given. That we don't know. We don't know what is a fundamental Hamiltonian. He'll never tell us that. So that is work for the future. That the theory should also tell what fundamental Lagrangian I'm going to put. So that will never be specific. Conservation laws, you mean? Huh? I'm coming to it. I'm coming, yeah. Like, Noether symmetries. Yeah, I'm coming. That's the central part of this whole mission. Okay. You can define a generalized Poisson bracket over the phase space. Now we have these Q's and P's, which are either bosonic or fermionic, and you can make a phase space of them. This is the Poisson bracket defined in analogy to classical mechanics. It can be shown to obey a Jacobi identity, and also time evolution equation for trace A dot is similar to what you have in classical dynamics. Okay, now come to your point. What are the construction of Noether symmetries will proceed in accordance to how we do it in dynamics. Let's just find out what are the invariances. And although I won't go into it, I should say we are working with the Poincare invariant theorem, and that can be taken care of. Okay. The trace Hamiltonian is conserved. That is quite obvious from here itself. It's time independent. You can see if you put A equals H, you get a conserved quantity. That's standard. There is another conserved quantity. I will not go into the details of its calculation. We do have a long way to go. So I don't have calculations. I'm sorry for that, because I'm going to condense this book into 2 lectures. So, okay. So this object has some analogy with the fermion number operator. So if you take fermion degrees of freedom, then this sum, I made a mistake, this is an anti-commutator, I'm sorry. Okay, and summed over fermionic degrees of freedom and then traced. If we define this quantity n, is called the trace fermion number. This is a conserved quantity. When we go to the thermodynamics, it will play the role of chemical potential. So in the thermodynamics and the statistical mechanics, we'll have the Hamiltonian and its corresponding temperature. Then we have another temperature which is like chemical potential corresponding to n. We'll bring that in. So this is the second conserved quantity. Now let's say come to what you probably call the most important part of this project. There is a third conserved number which I've been harping about, which they used this symbol C tilde. It's a very funny symbol which Adler uses. So this is object C tilde. In our review, we called it the Adler-Millard charge because Millard was Adler's student who during his PhD thesis discovered this conserved quantity C tilde, which is central to the emergence of quantum theory. The way it comes about is that the Lagrangian or the Hamiltonian are invariant under a global unitary transformation where if U is a constant, say n by n matrix, and you subject each of the dynamical variable to this transformation. Okay, again, sorry, this is H, it should be P. If it's a Lagrangian, of course, then it's Q dot, I'm sorry. This should be P. Okay. So as a result of this, this again I don't prove. Your proof is there in the book. It's fairly short. As a result of this invariance under this global unitary transformation arises a Noether charge. What is its structure? Sum over bosonic degrees of freedom of the commutator QRPR minus sum over fermionic degrees of freedom, the anti-commutator QRPR. We should look at this for some time. I think it's a beautiful object, very unexpected. What would happen if you're dealing with point particle classical mechanics? Q's and P's would be just numbers, they would commute, so C tilde would be identically 0. But here it is not. Also notice that each Q and P have an arbitrary commutation relation which would change with time as the time evolution takes place. So each of these commutators or anti-commutators is arbitrary, and yet this net sum is conserved. The next important thing is, as you can easily see, it has dimensions of action that sets us thinking. It the same dimensions as H bar. Now beginning to bring words in, because we have to remember we are looking at the quantum theory that we want to have QP commutator as IH bar or anti-commutator as IH bar. So looking ahead, what will happen in the thermodynamics is that this conserved quantity gets equipartitioned over all the degrees of freedom, one moment, and hence has the same value. So with certain caveats and reasonings, all these commutators, their canonical averages in thermodynamic equilibrium are equal to each other, and I'm allowed to set it to some constant which we identified lines from. Each of these. No, this is Hamiltonian evolution. This is, yes, right. Yes. There's a Hamiltonian evolution. Yeah, I could open it out. So it will be Q dot PR plus QR P dot, and I can substitute for that from the Hamiltonian. Yeah, but not arbitrarily. You are right. You are right. You are right. They obey dynamics. Yeah, I am sorry. Yes. It's not arbitrary. Subject to initial conditions follows dynamics. The matrices. No, no, no. Bosonic sector and fermionic sector. So there are two kinds of matrices, which is what these are. I say if Q and P are bosonic matrices, then I take a commutator. And these are matrices or operators, we use that. Okay, so before we go over to the thermodynamics, some more standard things. On the phase space, I need to define a measure because we are going to now go to the phase space, make a canonical ensemble, do thermodynamics with it. The measure is defined in a fairly intuitive way. XR is a phase space variable, QR or PR. Just as we do in classical mechanics, it will be like dq1, dp1, dq2, dp3, and dp2, and so on. I mean, two n-dimensional measure. It is the same object here. You have a product over R, and then you are also, you know, if it's a matrix, you are separating out each and every matrix element. I mean, that's like a further degree of freedom. XRMN is split into real and imaginary parts, and if you take A equals 1, it's the real part. If you take A equals 2, it's the imaginary part. You multiply everything out. It's fairly intuitive thing. It can be shown that this measure is invariant under canonical transformation. So we have a Liouville's theorem, as a result of which under dynamical evolution, the measure d mu remains conserved in phase. The phase space volume remains conserved as a set of system points expands. So d mu of xr plus delta xr is d mu of xr. And you can separate the bosonic and the fermionic. Okay, so this is the classical mechanics. Now we move to the second part, the important part, which will where we see the emergence of quantum field theory. Okay. In principle, in methodology, the construction of the canonical or the microcanonical ensemble is just standard statistical mechanics. But because of this C tilde, which is lurking around, new things happen. So I forgot to mention that this object has C tilde has further properties. It is anti-self-adjoint, that can be shown, and it is traceless. So these things keep on getting used in the analysis. Okay. So like we do in StatMech, we assume that you have a system with a very large number of degrees of freedom, these Qs, which evolve in phase space, and sort of assume the ergodic hypothesis. The system forgets its initial distribution over time, and time averages are assumed to be equal to statistical averages over an equilibrium ensemble. Some of this Dustin talked about. Yeah, similar to what he was talking about yesterday. And the equilibrium is found as usual by maximizing a combinatorial probability over various microstates. Essentially maximize the entropy subject to conservation laws being held. So C tilde, Hamiltonian, the trace fermion number have to be conserved, and that is taken care of by bringing in Lagrange multipliers when you are maximizing the entropy by varying the probability density rho, which we construct as defined in the first equation. The probability dp of finding the system in a volume element d mu in phase space is dp equals d mu times rho, which is the probability density, the density function. XR is, as I said, a phase space degree of freedom. So we have a whole bunch of XRs. And as we can, of course, we know in equilibrium, the phase space density distribution does not evolve in time. Rho dot should be 0. Okay. And as in StatMech, rho depends, apart from these dynamical variables, it also depends on conserved operators like C tilde, on conserved trace functions, constant parameters. We'll come to that. Okay, so now we start building this rho, this phase space density. We want to talk of thermal equilibrium. We have to choose a frame. So choose a frame in which the ensemble, the statistical ensemble, all copies of it are at rest. No translation, no acceleration, no rotation. So the charges associated with Poincare symmetry will all be put to 0. We have chosen a special frame. This is an important point. It is fairly subtle. So maybe spend 2 minutes on this. The original theory is Lorentz invariant, the trace dynamics. Now when you are making this ensemble, you have chosen a specific frame and broken Lorentz invariance because momentum has been set to 0. You have chosen the Hamiltonian in a specific frame. And Adler suggests that that is the cosmological rest frame in which CMB, the microwave background, is isotropic. This is, again, a very subtle point, I think, left for the future. So we do need a preferred frame, and that may have some implications later when we, for example, talk of trying to make collapse models relativistic. However, for the time being, this does not act as a disaster, this choice of the special frame, for the following reason, that this C tilde actually is a Poincare invariant quantity, and that is not affected by this choice of, particular choice of H for the following reason. As we go along, what we will do, we will assume that we are working at a sufficiently low energy scale. The temperature corresponding to H would be assumed, this is an assumption, assumed to be the Planck temperature. And when we come to much lower energy scale, the dynamics decouples from H. It is determined, the canonical averages are all determined by C tilde, which is Poincare invariant. So as a result of that, the quantum theory which will come out, that is Poincare invariant, although there's a choice of special frame, a bit of subtle reasoning. Okay, so the distribution function in the second equation, it's a function of these C tilde, H, N, those are our conserved quantities, and their corresponding Lagrange multipliers, tau, which is the analog of the inverse temperature. Eta here plays the role of a chemical potential. And the important object that has come in is this lambda tilde operator, which is the Lagrange multiplier corresponding to C tilde. And C tilde is anti-self-adjoint, so is lambda tilde. And it can be shown that these two operators, lambda and C, have to appear in row in the form as a trace of lambda tilde c tilde. Now this lambda is a new beast. You have analogs of eta and tau in standard stat mech. This lambda is a new thing, and stuff happens as a consequence. Lambda is an anti-self-adjoint operator. As of now, only that is assumed. More we will see now. All right. So define the ensemble average of an operator O in the usual way. Average over the phase space measure, the density, phase space density times O, that is standard. Okay. Now it can be shown and sort of easy to see also. O is an operator. If you take its ensemble average, it has to have an operator dependence, but there's only one operator around, that's lambda tilde. Sorry, this is not a bar, it's tilde. There's no bar here. So this operator average can depend on, tau and eta, but they are not operators. The operator dependence is only through this operator, some operator FO made out of lambda tilde, as a result of which lambda tilde and this O average will commute with each other. Now choose O to be C tilde. So we'll have lambda tilde and C tilde average commute with each other. That leads in a few lines, which I don't have a proof for, to some very important results. C tilde, we remember, is anti-self-adjoint and traceless. Lambda tilde is anti-self-adjoint. As a consequence of the fact that C tilde average commutes with lambda tilde, it can be shown that C tilde average can be written in this form. It can be written like this. It's a product of two operators, one D or D effective. Please ignore this subscript effective for now. The product of two operators D, where D is a real diagonal matrix with the non-negative element. This is a statement which can be proved. I is behaves like a unitary diagonal phase, phase and magnitude in quotes, and they have the following property. So there should be an average here. It can be written as a product of these two matrices. The trace is 0. I square, I is anti-self-adjoint. I square is minus the identity, and this is the statement here that these two commute with each other. Okay, so now we have structure emerging from here that notice that this D, or D effective, is diagonal. All elements are non-negative. What they will be depends on, the Hilbert space. You have a space of state vectors in the Hilbert space, which would determine what these elements of D are. Now comes in an important, very important assumption that for some reason the dynamics and its averaging does not favor any one state over the other. This is a very, very big assumption attributed to initial conditions at the Big Bang. But this is one caveat which we must ponder over in the future. What is this doing here? If you do that, if you assume that no state is favored over any other state, then all elements of D should be equal, and C tilde average just becomes, D effective can be written as a real number, positive real number times the identity, which multiplied with I effective is just I effective. And so C tilde average becomes a constant times I. So you can see what's going on here. deliberately calling that constant h bar. Later on it will turn out that the commutation relations obeyed by these canonical averages are QP average equals IH bar. Then you say, okay, please accept that H bar is the Planck's constant. So why? Of course, its value has to come from experiment. But it's interesting in a way that we did not start from a classical theory and then made an ad hoc quantization where Poisson brackets are replaced by, we say, QP Poisson bracket, let's replace it by QP commutator equals IH bar. So that is not what was done, as you can see. Rather, because of the presence of this conserved charge and this assumption that no particular state is favored over the other, you find that this average, which is eventually going to be equipartition, has a natural structure of being proportional to a real constant. And if you take C tilde average as I effective times H bar, put it in the equations in the above two lines, you get that trace I effective will be equal to 0. And because I effective square is minus the identity, because it's anti-self adjoint, it takes this form. It's I times a diagonal. Since the trace should be 0, we have to have a even number of these pairs. For every one, there should be a -1. And this has some future implications. The 1 will give rise to the commutation relations in our universe. The -1, very speculative, is a so-called shadow universe, which we will hide under the rug for the time being. Maybe we'll talk more about it tomorrow. Okay. So now, after having seen the importance of this C tilde average, we can, in the usual manner, construct the canonical ensemble, maximize the phase space Boltzmann entropy. Subject to these constraints, total probability is 1. These things should carry average subscript here. So lambda tilde, tau and eta are Lagrange multipliers introduced with each of these conserved integrals, which you add to the expression for the entropy, vary with respect to rho, and as you know, you would get the equilibrium density distribution given by the second last line, where Z is the partition function defined in a fairly standard way, except that there's a new analog of temperature, this trace lambda C, which is carrying along and which is going to be very important. Okay, so we are ready now to get to the main thing. All right, so the motivation, according to Adler, is this to foresee this and compare it with what happens in the equipartition theorem. You have equipartition of energy over all the degrees of freedom. You're getting a half kT for each of them. And the expectation is that because C tilde and lambda tilde are appearing in a way similar to tau h, there will be an equipartition of C tilde, which would be enough now that we know it has this structure I times h bar. If you are going to equipartition it over all degrees of freedom, you can expect the standard commutation relation. Okay, so let's compare it with what happens in the equipartition theorem. If you see the first integral on the left, it is a variation with respect to a phase variable of x times e to the minus beta h. This is not related to what we are doing right now. This is a motivation. One way of arriving at the equipartition theorem in what is known as comparable to what we do with word identities in quantum field theory, where you arrive at certain let's say quantities by variations of functional integrals with respect to, let's say, system degrees of freedom. So when in the left hand side, the integral is total derivative of some function. So if the function dies down sufficiently fast at infinity, this left integral would vanish. You can expand the integral as in write it as a sum of two terms. Del xr by del xs would give you a delta function. And then the phase variable acts on beta h. That gives you the last term on the first equation. The left hand side is 0. So the two right hand side integrals are equal to each other. You pull out the delta Rs, and delta Rs is equal to this stuff on the right in the second equation, which is easy to see. It's the equipartition theorem. You can check for yourself. Beta is 1 over kt. If you take h as a quadratic in, let's say, q square or q dot square, this would give you the equipartition theorem. Okay, so the motivation is that we will now try to do for some suitable function which is cleverly chosen, made out of these degrees of freedom and conserved quantities. We'll do a certain variation on it in the spirit of the equipartition theorem and derive results which look like this, but we will essentially get quantum theory out of it by doing a certain so-called word identity or equipartition. And as I said, the conserved charges are playing the role analogous to energy. And let's see what happens as we at low energies. If we neglect the h tau part of the partition function after doing all the variations, you have everything being determined by c tilde lambda tilde, and that in the average is quantum theory. Okay. So the analog of the equipartition theorem is that if you make a constant shift of a matrix variable xr in the phase space, to go from xr to xr plus delta xr, then, again, pardon this cap on mu, this the ordinary mu, I don't want to go into it. The variation with respect to a phase space variable of this quantity rho times O, again please ignore that J, I'm sorry for the moment, I'll just say what it is. The variation of rho O, where O is some operator we are going to choose, is 0. That's the analog of how the equipartition theorem is built, how we construct the so-called word identity. Now choose O to be this particular operator, C tilde I effective anti-commutator times some polynomial made W made out of the dynamical variables. This is a very clever choice. I don't have a physical way of seeing how they guess that this is the fellow you should be working with. All the quantum dynamics comes out of here now with this choice of O, and different choices of W give you different important things. So we do a variation of rho O. So the second line, I have substituted the expression for the partition function, except that I've added here what are called source terms, I mean, which is variation with respect to this source terms, gives information about canonical averages. In the end, the source term J is set to 0. This is standard in StatMech. So let's see what is the structure. exponential starting with this bracket closing here. This is the partition function with source terms included for each variable x times j. J is the source, and multiplied by trace here, trace of this fellow, all right? So I have to do a variation of this whole thing, all right, where O is making sense? Delta XR is sitting on the outside here, and that is this fellow, and variation of rho times O. Rho is here, and O is this object. Now I'm a bit confused where I got this trace in from. Please pardon me for this. I don't see the need for this object. Okay. Anyway, I hope you get the idea of what is being done. For a suitable operator choice O, okay, you do this variation. Now that's a long calculation, but at least in principle, I hope you get the idea what is being done here. Okay, now we make some important assumptions to simplify the results. One is that the energy scale tau inverse, where tau is the inverse temperature associated with the Hamiltonian, with the energy. The energy scale tau inverse is the Planck scale, and we are working at much lower energies. This is needed to simplify what is going on. We don't want to worry about that rest frame issue. We want to get the Hamiltonian out of the averaging consideration. The chemical potential eta can be neglected. That's also an assumption. We won't go into that right now. The third assumption is very important. We have to take note of it. The charge C tilde is replaced by its average value, which you already seen is I effective times H bar. So you want to do this variation, apply these three assumptions, and see what comes out. And then, do you have any questions? Is this confusing? Did I put you to sleep? Are you okay? No, are you okay? No, I'm not saying you're sleeping. I'm saying see, this is a standard StatMech procedure. It's a bookkeeping device. You add in, this is the source current times the phase variable kind of term. You do a variation, and in the end you set J to 0. It helps you get what you want. Okay, if you look up, huh? Yeah, okay, you can say that. After doing a thermodynamics of it. Canonical averages will be identified with fields. I'll come to it. Underlying theory has these Q's and P's. Now I'm going to get their canonical averages. Those averages obey the rules of quantum theory. But I broke Lorentz invariance by going to a specific frame. And now I neglect this tau inverse, again come to a sector which continues to be Poincare invariant. There is a caveat that in between you have lost or Lorentz invariant, but you still get out of Poincare invariant theory in the end. No, it's a selfish motive. You want to, ordinary quantum theory works at much below. It could be any scale, stay much below that. No, no, no. It's just that, it's a natural thing to do. It's something that nobody has seen. So we don't know what's the physics of trace dynamics. So hide it. No, the emergent theories at low energy scales, the scales should be much lower than Planck energy. The original theory, no. Original? No, no, no. That doesn't pick up any energy scale. Here. Yeah, but we'll have a problem. It's like this. If you want thermodynamics of a box of gas, you're obviously working on scales much larger than the scale of atoms. If you say that I want thermodynamics on the scale of atoms, you'll have a problem. So we are now coarse graining over the atoms, which are these trace dynamics degrees of freedom. And the box of gas is the quantum theory which will emerge after average. So we have to do a separation. Certain? Okay, let's go through this. I only have 2 more slides. Then I think that might answer your question. Okay, so from this variation, with these assumptions, I'm going to get an analog of so-called equipartition theorem on a Ward identity, which is this first line. The canonical average of the operator D acting on a phase variable xu vanishes, where dxu is defined on the right-hand side in the first line. I effective times the commutator of this polynomial w with x2 minus h bar, which came because I replaced c by c tilde average, times sigma s matrix omega us times the trace derivative of trace w with respect to x. Omega us, if you remember, if you want to write Hamilton's equations of motion as one equation other than 2 equations, you have to introduce this matrix 0, 1, minus 1, 0. Okay, it's just a bookkeeping. This is a constant matrix which is made up of block diagonal elements 0, 1, minus 1, 0. It's just a bookkeeping. Okay, this is a very important equation. It is everything. So to put it in a dramatic way, this is quantum theory. We'll see that slowly. We make 2 different choices for W. First, take W to be the polynomial from which the trace Hamiltonian was constructed. Just put in W in the first line in this Ward identity, and you will see that dxu is equal to I effective times the commutator hxu minus h bar. Now, where has this x dot come from? This is very interesting. W is h, so trace w in the last term on the first line is trace h, and this sigma that is sitting in there, those are nothing but Hamilton's equations from trace dynamics. So there's no averaging over there. So del h by del q would be something like p dot, del h by del p will be q dot, suitable sign. That is this what is giving rise to this x dot here. This x dot is coming from here by using trace dynamics equations of motion. Okay, so that is interesting. This is if you choose w equals h. This is the form of this operator. Its canonical average vanishes. which means if you take a canonical average, the average quantities are obeying Heisenberg equations of motion. This was, as you see, this was not there in the beginning. This was not a trace dynamics equation. Trace dynamics equation was just ordinary Hamilton's equation, but now we have gotten in a commutator. So at this stage, one can ask a very interesting question. We are at thermodynamic equilibrium. Rho dot is 0. How did we get a dynamics out? We have information about dynamics, that you got Heisenberg equations for the variable, so that is x dot. So the important thing, the reason that has happened is not that anything is evolving, nothing is evolving at equilibrium, but you extract information about the time variation of these phase variables from here, because the phase dynamics equations of motion in Hamilton form are first order. This gives you a x dot, which is the same, and this is coupled to this commutator, which is the standard Heisenberg operator commutator in Heisenberg equation of motion. This fellow is sitting here, and because this is related to this, because the whole thing vanishes on averaging, because this relates to trace dynamic equation, is how you get information about the dynamics. So this is very interesting. You are at equilibrium, still you extract information about time evolution. Okay, then similarly, go to the next step. Take W as a C number times phase space variable, substitute it in the word identity, which is in the first line, and just work everything out. Yes. Somewhere? Yeah. Here? Here? XU? I just put this, no? That's W. Okay, it will come out, yeah. Okay, so then if you simplify this out a bit, it can be shown that you get, it looks like magic, but this is the equipartition theorem. These double wedges stand for commutator or anti-commutator, depending on whether it's a boson or a fermion. So you get out what you want. These canonical averages obey standard commutation relation. Suppose you have one more step. You have to, as you were asking, relate this to quantum fields. So right now this is canonical averages. So for that, we sort of by hand, we have to make an assumption, make a map. This is my last slide for today. So we actually assume that there is a correspondence between operator polynomials in trace dynamics and operator polynomials in quantum field theory. And the quantum field variables are denoted by capital X. So make an assumption that if this is a polynomial in trace dynamics, we can, this is an assumption, map it to a polynomial in quantum field theory. Okay, and in the second line, now we start making a map to, let's say, what are known as Whiteman functions in field theory. The object on the right-hand side, the vacuum expectation value of this polynomial made out of quantum field degrees of freedom, capital X. On the left-hand side, we assume that the Hamiltonian, the trace Hamiltonian is bounded from below, and psi naught is the, the ground state, the lowest energy eigenvector of H. Okay, so the second line is also an assumption that this element on the left is mapped to something in quantum field theory. So that is how you actually introduce a map. If you accept these first and second line, then the third and fourth line will follow, okay, because you have mapped canonical averages to vacuum expectation values. You will get the standard commutation relations or anti-commutation relations for quantum field degrees of freedom. You'll get the Heisenberg equations of motion for them. And lastly, once you have the Heisenberg dynamics, you can make the transition to the Schrodinger picture in the conventional way. That doesn't involve trace dynamics. If you have recovered Heisenberg dynamics, then the way we normally do, how to go from the Heisenberg picture to the Schrodinger picture, the same thing we do here. Okay, so this takes care of step 2. This we will come to tomorrow. But I need Angelo's lecture. I want him to talk about collapse models. And then we want to derive collapse models from trace dynamics. So we'll come to that. So I hope it was not too ambiguous. Okay, I'll stop here. We can have questions or we can go for lunch. Yeah?
If trace dynamics is a correct theory, so we can kind of think that all the fields are kind of composite classical fermion field.
Okay, now we go slow. See, the underlying theory is a classical theory that gives me time to make another comment. This is not a hidden variables theory because you have classical degrees of freedom, the trace dynamics degrees of freedom, which have additional information compared to canonical averages. The average system does not know the underlying system. But because those underlying degrees of freedom are at a different, so to say, level as compared to quantum theory. Quantum theory does not, in this language, does not involve trace degrees of freedom, but only their averages. So these two are operating at different levels. So it's not hidden variables. Now, I wouldn't say that these quantum degrees of freedom in this language are some kind of trace dynamics degrees of freedom. That's what's called emergent phenomenon. Just like say if you have superconductivity emerging from electron pair theory, you would not say that superconductivity is the same thing as one electron pair, or it's a consequence.
So quantum theory is kind of condensed matter physics of trace dynamics.
Yes, yes, perfect. That's in that sense emergent.
And other thing is that the scale, that you put Planck scale, that is quite random.
Yes. Oh yes. So let's see what are the various shortcomings so far. One was the assumption that all states in the ensemble are equally preferred. That's how you put that diagonal matrix to have equal values for all the elements and H bar. That's a big assumption. The second big assumption is that there is an energy scale tau inverse which separates our quantum theory from that scale. That's an assumption. Yes. We'll talk a little bit more about gravity tomorrow. Right now in this, there is no gravity. So, the sense in which gravity has been talked of as an emergent phenomenon is by showing that the Einstein equations can be written as thermodynamic equations. And hence, that there will be an underlying micros theory to which if you did the StatMech, you will get Einstein equation. You get what I'm saying? Well, there no one has told us what is the underlying theory. What are those microstates? What are those atoms? So I think that is not as well developed as this. It started from a micro theory. So at least in that sense, this system is more complete.
Considered as a micro-canonical ensemble.
You can do that. I did not do that. You could have done that and got the same. This is there in the book. Yes.
Okay.
A little question on the issue of candidate ontologies. You kind of said they should remain hidden. Well, that you should hide them because we don't know. But if I understand correctly, at any rate, they will always remain hidden because this happens on scales so small that even even the most elementary particle will not have.
Yes.
Yeah,
yes.
So this is
the scale is even more removed from than elementary particles.
So we will never have the debate that when thermodynamics and the issue of elementary atoms arose in the 19th century, people were saying it's a fiction, others it's not a fiction. But
say that again, I'm not getting
in the 19th century, when people, when the concept of atoms was suggested as being the origin of the thermodynamical laws, one common trend was to say that this hypothesis was a fiction.
until it was experimentally discovered.
Yes,
so that's a good point, yes. What would be the experimental signatures of trace dynamics? Something like that?
Yeah, well apparently that couldn't be possible, right?
Okay, two answers. If you go looking for those very primitive degrees of freedom, you would have to go to very high scales. Or one, if you allow that claim, which we'll see tomorrow, if these theories predict stochastic modifications like in collapse models, then you might say if you confirm collapse models, in a way you are supporting trace dynamics. Blah, blah, meaning, subject to. You have a question, Rafi?
Just a couple of questions to make sure that I understood. These Q's and P's, QR and PR, we should think of them as quantum field variables, is that right? They're not particle coordinates, as the notation might suggest.
You are right.
They're
you are
more
right.
like-
They are quantum field variables.
So they're like the configuration, like of a scalar field. Q's, R's would be the value of phi at
Yes.
a moment of time, and
Yes, yes.
P would be phi dot something.
Yes,
That's the
yes,
intended
yes.
application. The second question is, you said that one assumes equilibrium. And that, I guess, is it true that equilibrium is meant to represent the vacuum states? Or is it meant to represent all possible
All possible
states?
All possible states.
But somewhere you had vacuum expectation.
Yeah, actually, so here in the second line, that was introduced just to propose how we will map from trace dynamics averages to, let's say, Weightman functions in field theory. But this psi naught is just one of the psi naught on the left. This is the ground state of the trace Hamiltonian of trace dynamics. Did I get you confused?
I see. So
let's say,
in some sense, you're considering, I mean, these Q's and R's are out of equilibrium in some sense. I mean, you're following them in detail.
yes, but then
Even
I'm
though-
averaging, and it is these averages which map to quantum theory.
But you're not fully averaging the Q's and P's.
I am.
You are?
Yes. I mean, like in the Maxwell.
Then it seems like you wouldn't have any. I mean, if we say a particle in contact with a box of gases in equilibrium, normally we'd say it's that the gas is in thermal equilibrium, but the particle has non-trivial evolution. I mean, and just this is all classical, right? So if you were to average over the position of the particle too, you wouldn't get genuine change. You wouldn't get a genuine.
Are you asking where the dynamics is coming from?
Yeah, isn't it? Don't we have to assume that certain variables are in fact not quite in equilibrium?
Like the
Or to have
second
genuine-
line here, yeah, like where did my x dot come from?
Yeah.
Yes, so okay, so I think you probably had gone out at that time.
Yeah.
What's happening here, so we discussed this question, you have equilibrium, where did the dynamics come from? Yeah, something like that. So the first equation here has really no time in it. It is an equilibrium equation. Now, I'm not saying there is a dynamics actually operating at the equilibrium, but I can extract information about what the dynamics would be from this equilibrium equation, because if you look at the last term on the right-hand side of the first equation, those are nothing but the trace dynamics Hamilton's equations, which I exploit to replace that term by x dot. If there had been evolution, it would be described by Heisenberg.
That's a non-committal. You say if there had been evolution, but presumably you want to say that there really is evolution. And it's just,
I don't know how to. It's
these-
definitely a subtle point. How does one get information about evolution when one is at equilibrium? But at least in black and white, it is clear what's going on here. Maybe we should. This is a very subtle point. Yes.
So you don't think the description I offered before would be
It's not out of equilibrium, not so far. No.
maybe okay? Maybe it's a question of let's discuss later. Maybe it's a question of language, but my picture is something like a heavy particle in contact with a mass of light particles, and the light particles are on a shorter time scale, and they somehow remain in equilibrium over time scales in which the larger particle
No, I don't.
is not, because if it were truly, quote, in equilibrium, it would have to be nowhere, it would have to be described just
I
by...
think my answer is probably not fully crystal clear in the physical sense. It's only clear in terms of equations, but I should think more, maybe try to answer you better. I mean, I looked up what Adler and Phil Pearl have to say about this point. How did I get information about dynamics out from the equilibrium? And the answers that I have found are only at this level, that you sort of extract information about the dynamics from the structure of the way the equipartition theorem comes here. It's certainly not out of equilibrium. Not right now, not until we talk of fluctuations. I'll think more.
So perhaps vaguely related to this is also the question of how interference arises. I mean, we're used to at least thinking conceptually of classical theory and classical probabilities as emerging out of quantum interference, ecoherence.
Yeah.
But here, it seems to me, if I've understood correctly, that you don't start off with some theory which fundamentally has interference.
At the trace dynamics level,
Yes.
uh,
I mean, in other words, you really have a full underlying quantum theory with all of, with the quantum measure, the language we discovered.
yeah.
Basically, what we have learned to understand with quantum theory, that you must have interference.
I agree, but that's now in this language an emergent phenomenon.
Right, so the fact that you can go from something where you're talking about classical probabilities to...
No, there are no probabilities. There are no probabilities. It's a classical theory, but it is deterministic.
Right, so classical theory going to classical probability. So even at the level of, even if you did a statistical and a standard statistics of those of a classical theory,
At the lowest level,
you would get a classical probability theory. But then
yes.
somehow quantum probabilities or quantum interference emerges. It seems to be like somewhat topsy-turvy in the sense. And I'm curious how you would get, because we think of quantum theory and quantum probabilities as
Quantum probabilities we will come to. So that's the third part of the talk, when we talk of fluctuations around equilibrium. So right now we have only recovered unitary dynamics, which yes, exhibits interference. And at the level of interference, we do not have to talk of probabilities. You are asking how sort of this okay. But I think what's happening is that this classical theory, namely trace dynamics, while structurally the same as ordinary point particle mechanics, is actually a very different theory. I mean, think about it. It is, I mean, it has, for example, that new conserved charge. So I would not think of it as just a point particle classical theory. It's a highly non-commutative stuff. Because the whole point would then be that if it was exactly like ordinary point particle classical mechanics, I should not expect to get anything new. I would have to just do the standard canonical quantization.
So would it be right that the fact that you have these different, at the initial time you have these randomly chosen commutation relations
Yes.
In the phase space, that somehow is key to getting out interference at the emergent level?
Yes, yes, you can say that. You can say that. Definitely. I think that is a good thing you said. It probably helps answer your question. So to put it in a slightly different way, we want the operator structure to be there right from the beginning. Unlike in the standard canonical quantization where you have real number dynamical variables which you upgrade to operators, here you want to work with operators right from the beginning. So it's a classical dynamics of operators. I think that answers your question.